Okay, so this may be at any period t. So corresponding to a given hazard, okay, because frequent earthquake occurs, smaller earthquakes occur frequently, larger earthquake occurs rarely. So a larger SA at your structure will occur rarely, and a smaller earthquake will occur frequently. So it is only giving you the probability distribution of occurrence of different levels of spectral acceleration at your site. Now you decide for what probability you want to design. Then for that probability of occurrence for which you want to design, you can read the value of SA which you should consider in your design.
So this lambda is rate of arrival,
Rate of occurrence.
Rate of occurrence, and it is given in like 2% in 50 years.
2% in 50 years.
So how we managed to do in this?
Sorry, managed to do what?
Managed to do write this.
How do we get this curve?
No, lambda, x-axis.
So you can write here. Generally it is per annum. So if it is 2% in 50 years, how much will be in 1 year? Roughly, you will obtain using that formula which I have given between return period and this. But roughly, if 2% in 50 years, how much will be in 1 year? What is the probability in 1 year if we assume that it is occurring uniformly? 2 by 50%. Okay. So like that, so you can give 0.0001 or 1 into 1 minus 4, 2 into 1 minus 4, 3 into 1 minus 4. So like that, you will assign the probability of occurrence. Generally, it is annual rate of occurrence. Any other question? So, what we have got now is the capacity, which is given in terms of capacity curve, and capacity curve is nothing but base shear versus delta roof, and we get a curve. This is capacity curve of a structure. It is signature of the structure. Okay, so this is characteristic of a structure, and we have demand, okay, which is given in terms of response spectrum for a particular probability of occurrence. Okay, so this is demand, and this is characteristic of earthquake or site. Okay, this is hazard for a given lip of occurrence. So we know the capacity and demand both. We have to compare those, whether the capacity is adequate to meet this demand or not. How we can compare? Do you see any problem in comparison?
Yes.
Can we compare this with this?
No,
Why not?
because this is represented in time period. This is in
Because the axes are different. This is in base shear versus delta rho, this is SA versus T. So let us see, is there any relationship between these? So what we do is, we convert our our capacity into equivalent single degree freedom system. Okay? This equal single degree freedom system. This was our building. We have obtained its pushover under the first mode. Okay, we are converting this into an equivalent single degree freedom system. Okay, such that the capacity curve for the single degree freedom system is equivalent to that of the building. Okay, so here we have base shear versus delta rho. In single degree freedom, what we will have? The force will be SA, because what is SA? The force per unit mass. Okay, and displacement we will represent by ST. The displacement of the single degree freedom system is ST. The relationship between these two has to be such that the period is same. Okay, and I need period. K and M will be decided in such a way. Let us say I take M equal to 1. So then K I can calculate based on this period. K is M omega square. So 1 into omega square, that is 4 pi square, T1 square. So I can calculate the stiffness of this. Okay. So for unit mass and period same as this, I can convert this curve to the single degree freedom system. How? SA, here the total seismic weight is W. So SA will be BB divided by alpha 1 into W. What is this alpha 1? Mass participation factor in fundamental first one in that direction. So fundamental mode in that direction, which is first mode in that direction. So that is alpha 1. You remember the expression for alpha 1? In theory of vibration, modal mass participation you have done. What is that? Summation Wi phi I in the first mode whole square divided by Wi phi I in the first mode square summation Wi. And summation Wi is equal to total. SA and SD are
quantities same because it is convertible.
yes.
So as it is
It is convertible if you know the period.
yes, if I know the period.
Okay.
The
And
degree of freedom system.
hold on. For this single degree freedom system, which has, or this building, which is having this base shear versus delta rho, what is its period? First of all, is the period constant?
It will be fundamental combination of two modes. It will be.
No. Let's consider first mode only. We are considering first mode only. But problem is that the period is not constant for a nonlinear structure. So what you are saying that SA and SD are related, that is true for an elastic system. For an inelastic system, actually the period changes. Here the period is this much. Here the period goes on changing. So the relationship between SA and SD does not remain constant. Okay. So SA and SD, for an elastic structure, any one of the two you know, it will serve the purpose. But for inelastic structure, not. In elastic structure, you need to know the period at that value of ST, because period changes with displacement. Okay. So SA you can calculate like this, and SG you can calculate from the roof displacement, delta roof divided by gamma 1 into phi 1 at roof. The mode shape which you have used to develop the capacity curve. So delta roof you understand, and what is gamma 1? Gamma 1 is summation Wi phi 1 I divided by summation Wi phi 1 I difference is only numerator is square, the numerator is not square. And what is phi 1 roof? Phi 1 roof is the value of the mode shape or the coefficient of the mode shape at the roof. And you know, suppose I am taking a linear mode shape. A 4-story building. I can take it in proportional of the height 3, 6, 9, 12. I can take it as 1, 2, 3, 4. I can take it this as 1, this as 1 by 4, this as 1 by 2, this as 3 by 4. All three are phi 1. You agree? All are motions. First motion. All are representing the same motion. Will gamma 1 be same? Do it. Assume the Wi to be W same. Do it. Calculate gamma 1 in these three cases.
We have a graph between VP and delta rho.
Right.
We know the VP is equals to AH into W.
And what is AH?
AH is the acceleration as the height is the
No. It is not really. That is a design base. That base shear is one value of the base shear which you have designed for.
That is the capacity.
BVD, actual base shear will vary. It will depend upon the displacement, how the hinges are forming.
Yes.
And it will be higher than what you have designed for. So BVD is AH into W, but actual base shear
More
it
than.
depends on the displacement, and it will be usually more than that, because there is some hidden capacity.
Hidden capacity in terms of plastic hinges?
No, hidden capacity in terms of characteristic strength, because you have used characteristic strength, whereas we are using expected strength.
Yes, sir.
Secondly, we have used factors of safety while designing.
Yes, sir.
Here we are not considering factors of safety. So this value of BB, the maximum value of BB you will get from pushover analysis will be more than what you have designed for. And what is usually the ratio? 1.5 to 2.5 in that range. If you are designing as per Indian code, that ratio will be somewhere 1.5 to 2.5. Because there may be some additional hidden strength also, because you might have provided reinforcement more than what was calculated for BB. And then you have used strong column beam design. So size of the columns might have been increased more than what you were doing capacity due to capacity design. So due to that, the actual strength will be higher than what you are calculating from AH into W. And there is a non-linear relationship between base shear and displacement. That's what we have done in more than half of this course. So BB is not AH into W. It is variable. BBD is AH into W. But thank you for asking these questions. It's good. Yes. So how much is gamma 1? 1 point?
0.11.
अरे एक आदमी तो क्लियरली बोल दो. 0.11. Second?
1.33.
0.33 or 1/3. And this one? 1.33. So will my SD be same if gamma 1 is changing? Okay, so calculate gamma 1 5 and roof now. How much is that? Find 1 multiplied by 12. 0.33 multiplied by 4. 1.33 multiplied by 1. You will see gamma will depend upon the scaling of the load shear. But gamma 1 into 5 and roof will become independent. And it will be in this range only. Whatever structure you take, even if you are taking parabolic, it will be somewhere between 1 to 1.5. In that range you will get. And what it is actually representing physically, what this gamma 1 5 and roof is representing? It is representing the relationship between the displacement which you are getting here to the displacement you are getting here. So the relationship between these two displacements, displacement of a single degree freedom system and the roof displacement of the multi degree freedom system, that ratio between the two, that is gamma 1 phi 1. And you can see, irrespective of the building height, this ratio will be somewhere in this range, 1 to 1. Okay, you can try this for 20-story building, considering a parabolic motion. You will see that will also come out to be somewhere in this range. Okay? Yes.
From converting this multi-degree freedom system to single degree, I have to decide height of the single degree freedom system. That how can I decide that?
You write down the equation of motion of the single degree freedom system. Please do that. Everybody. What properties we need to write down to solve the equation of single degree freedom system?
Strictness and mass matrix.
We have mx double dot plus cx dot plus kx is equal to minus m x double dot. Okay, you divide this by m, x double dot plus c by m is how much? X dot plus omega n square x is equal to so what do you need? You don't need m, you don't need k, you need omega n, period. So as long as period is same, it doesn't matter what is the height of your single degree freedom system, what is the stiffness of your single degree freedom system, what is the mass of the single degree freedom system. If its period is same as that of a building, that is important. So the period has to be same. So if it is having the same period, the relationship okay between this displacement and this displacement will be same. We don't need any other term. Okay. So when we convert the multi-story building into equivalent single degree freedom system, we can get the capacity curve in terms of SA versus SD, because SA is nothing but B versus alpha 1 W and SD is nothing but delta rho divided by gamma 1 phi 1. So gamma 1 phi 1 roof is a constant, alpha 1 W is a constant. Okay, so what we are doing actually? We are only transforming the axis. So we will get a curve, a similar curve, only the axis will be transformed. That's it. When we convert this into this form, we call it capacity spectrum. Earlier it was called capacity curve, now it is capacity spectrum. Because now it is representing the behavior of equivalent single degree freedom system. So from the behavior of building, we have obtained behavior of equivalent single degree freedom system. Okay, this is also called acceleration, displacement, response spectrum. ADRs. Acceleration, displacement, response. And we can also represent our response spectrum, the demand, also in SA versus SD. Can we do that? Here we will use the relationship which you were talking. So in this relationship, what we will do? Corresponding to every period, I will take different values of period, and corresponding to every period, I can calculate SD. So I can calculate SD, and rather than plotting SA and D, I can plot SA versus SD. Okay. So SA, SD and D are correlated. Out of these three, two are independent. So any two you can take independent, third one you cannot take, because this relationship exists. If you know T and SD, you can calculate SA. If you know SA and T, you can calculate SD. Okay, and vice versa. One more thing, here a vertical line is representing constant T. Here, which line will represent constant T in SA versus SD? If T is constant, what will happen to that equation between SA and SD? SA is SD into 4 pi square by T square. T is constant. So what will be this equation? This will be a straight line, not at 45 degrees. The angle will depend upon the value of T. Okay, but it will pass from origin. Y is equal to mx plus c. So c is 0. Okay, so constant T lines will be like this. T1, T2, T3, T4, T5. And those values of SA which you have plotted there, you can plot here. There, these T lines were vertical lines. Here the T lines are inclined lines passing from the origin.
Sir, can you repeat?
These are our T1, T2, T3, T4, T5, and T. Corresponding to each T, there is a vertical line. Okay, at this line you can get the value of SA and you can get the value of SD. Now look at this relationship. SD is SA into T square by 4 pi square, or SA is equal to suppose T is constant, 0.2 second. What will be this line? SA is equal to SD into some constant. This is the equation of a straight line passing from the origin. So in SA versus SD graph, constant T line will be inclined line. Slope of that line will depend upon the value of T. Okay, but it will pass from origin. So that's how I have plotted these lines, and then the same response spectrum I can plot. So ADRS is the format in which you can plot demand as well as capacity. So demand as well as capacity, both you can plot in ADRS form. Once both demand and capacity are plotted in the same format, now you can compare. The capacity and the demand. We can compare, but still there is one problem which we have to solve, and that problem is that this response spectrum is corresponding to 5% damping. Okay, this equivalent single equilibrium system which we have considered, what is the damping here? The damping actually varies. The damping depends on the energy dissipation. So we have Xi equivalent of the single degree freedom system, that is Xi naught, the material damping, plus hysteretic damping. Xi naught, the initial damping, that may be 2%, 3%, 5%. Okay, depending on the material, so that is 2 to 5%. Generally we take 5%.
Hysteresis damping goes by
Non-linear behavior, because what will happen, suppose the displacement is this much, So what will happen? There will be, when unloading will occur, we will get a loop like this.
Non-linearity in terms of material and geometry. Materials, material damping we have considered. And so the remaining is the geometrical non-linearity.
No, but this is not the complete material. Even if your material was not yielding, suppose material is elastic.
Yes, sir.
Is there any damping?
No, sir.
No.
Sir.
Elastic systems. If I have a building, single story building, I give it a small displacement so that it does not go into non-linear range.
Yes, sir.
Will it continue to vibrate forever?
No.
It will come to rest.
Yes.
Which property is responsible for that?
The damping because.
Damping. So even if your material is elastic, there is certain damping.
Yes, sir.
How much is that damping? What is the order of that damping? What you have studied in your theory of vibration class. In theory of vibration class, you have studied only linear elastic system, vibrations of linear elastic system, and every system you were considering damping. Okay, so this 5% damping which you are considering, this is elastic damping. Hysteretic damping is in addition to it, which occurs because of the hysteretic loop, the energy dissipation due to inelastic behavior of the structure. That is hysteretic damping, which is in addition to it. And it will depend upon the area of the hysteretic loop.
It will be between the load versus displacement.
Sorry?
The energy which is dissipated means we can evaluate it in terms of load versus displacement.
Yes, that's what we have done.
Yes.
This SA versus SD, because SA is some factor times load and SD is some factor times displacement. So this is also representing
Load versus displacement.
load versus displacement, and the energy dissipated in each cycle is equal to the area of the hysteretic loop in that cycle.
The cause of displacement in plastic range is governed by the geometric nonlinearity.
Geometric nonlinearity is
Means the displacement governed in plastic range is by due to the geometric nonlinearity.
geometric nonlinearity is also there. You mean period like that.
Yes.
But more than that, it is the lateral force. If lateral force is not there, if earthquake force is not there, why there will be lateral displacement delta, and why there will be P delta? So P delta also, while developing this capacity curve, we have considered P delta also. But more than that, it is the earthquake force, the demand. Larger demand, more displacement. Lesser demand, less displacement. So this demand itself, we are trying to find out that how much displacement in my structure is occurring. This comparison will give me what? It will give me that actually how much displacement will occur in my structure. Okay. So initially I do not know. Why I do not know? Suppose I consider this as the displacement. So at this displacement, the size of the hysteretic loop not like this actually. It will be like this. Okay. So this will be the area of the hysteretic loop. So more energy will be dissipated. And this is definitely going to be more than 5%, because 5% was there even in elastic range. This response spectrum I have plotted for 5%. So the damping in my structure is going to be 5%, more than 5%. So it is not justified to take this point. Okay. I should take the demand corresponding to the damping, total damping or equivalent damping here, which is present in my structure. Okay. So I need to calculate xi hysteresis. For xi hysteresis, there is a simple relationship given by Chopra in his book. With xi hysteresis, we can calculate as 1 upon 4 pi ED over ES naught. What is ED? ED is the area of this hysteretic loop. So if you calculate area of this hysteretic loop, that will give you ED. And what is ES now? If you join this point with a straight line, then the area this area. This is ES. So area of the triangle, if the structure was elastic and we were getting the same displacement in the elastic structure, then the energy stored by the elastic structure at this displacement, that was ES. So elastic structure would have moved to this point along a straight line. Inelastic structure has gone like this, elastic structure would have gone like that, and elastic structure would have stored this much energy, what is given by this green area.
Yes, was the secant stiffness and delta.
1/2
Yes, 1/2
2 into this force times delta. Okay, this is area of triangle. Simply. So you can calculate xi equivalent.
And sir, the area of EB is the tangential stiffness.
No, it is area of the shape. You can't get it from tangential stiffness. You have to consider the whole shape. Okay, so here the equivalent bilinearization comes to our hand. That's why, because if you have to consider the actual loop, you can do it geometrically.
Yes.
Okay, but we can simplify it if we represent our capacity curve by equivalent bilinear. So our SA versus SD, the capacity spectrum is like this. We will represent it by equivalent bilinear. Now at any displacement, here the hysteretic loop will be like this. Now you can get this area easily. This is our E. ES naught this is ES and xi hysteretic and xi total xi naught plus
TB over TS not always greater than 1.
check it. You can see it. Can it be less than 1? But do not forget that 1/4 pi is also there.
TS not using the energy which is
ES naught is the energy which will be stored by the elastic system. Elastic system is not dissipating, it can only store. And when you relieve it, it will give you back that energy. Whereas ED is the energy dissipated by an elastic system. Inelastic system will store some energy, it will give back some energy, but part of it will be destroyed. It cannot be destroyed, it will be converted into another form of energy, heat.
So dissipation of energy with respect to the stored energy.
So if we take the ratio of these two, the energy dissipated by the inelastic system and the energy stored by an equivalent elastic system to undergo the same displacement. Okay, then this xi hysteretic can be calculated like this.
Sir, if elastic structure is not going to dissipate the energy, then why we are adding to the damping?
We are not adding that.
Yeah, that's
We are adding xi hysteresis. Xi hysteresis is coming because of the inelastic structure.
No, no.
Not because of elastic structure.
Total damping equal to, you have that xi naught plus xi hysteresis. That xi naught is the elastic damping.
So same structure when it is elastic, that much energy it will continue to dissipate. In addition to that, if it goes into an elastic range, see, structure has some energy capacity even when it is energy dissipation capacity when it is elastic.
Yes.
When it goes into an elastic range, the capacity increases.
Yes.
That capacity will remain. That capacity is not going anywhere. In addition to that, it has additional capacity. So xi naught is when it was in linear range. Okay, this will continue. Additional capacity it will get because of the hysteresis.
That xi naught and ES naught is same or different?
No, it is not same.
ES naught is what?
ES naught is this area and xi naught is the damping. ES naught is just this area. Xi naught is not ES naught. Yes.
This xi hysteresis only will be in the case of cyclic loading.
Yes.
In case of not, it will be
No, no. So only in case of earthquake, which is hysteretic, I mean, which is cyclic load, there it will happen. Yes.
Demand and capacity curve, we still cannot compare because we plotted the demand curve based on that constant equation of SI. But capacity, the equation is changing.
Right.
We still compare.
We will compare. We will discuss that. First I am giving you the issue. So one of the issues there was that demand curve has different damping. The blue curve was having different amount of damping. This will have different damping, and the damping goes on increasing as the displacement increases. The demand curve is plotted for 5% damping. So what I have to do? I have to adjust the demand curve for the damping actually present. Okay, so you know response spectra you have plotted. Suppose this response spectrum is for 5% damping. What happened to 2% damping? It increases. What happened to 10% damping? It reduces. In 20% damping, it reduces further. In 30% damping, it reduces further. How to get these reduced response spectra? Any method you know? This reduction, this is equal to R. Okay. In IS 1893 part 4, a table is here. Earlier that table was there in part 1 also. 1984 or even in 2002, in part 1 also that table was there, where you can convert the response spectrum given at 5% damping. Code gives at 5% damping. But if you need at any other damping, you can multiply by a factor. Okay, damping modification factor, R psi, and Euro code ECA gives an expression for R psi, and that is equal to 0.1 divided by 0.05 plus xi equivalent or xi total whole to the power 0.2. Xi equivalent is to be put in fraction, not in percentage. Okay? So for 20% damping, let us say, can you calculate R psi? Put xi total as 0.2, 20% damping, how much will be the reduction? So you can use either the table given in our code, or you can use this expression given in our given in Euro code. If you look at ATC 40, there is a different definition, different value, and if you look at FEMA 440, they have come out with different value. Why? Because these have been obtained empirically. So they have done it for different systems, different earthquake ground motions, and they have seen how much reduction occurs. So different ground motions result in different reductions. So this depends to some extent on the ground motion also, what type of ground motion we are using. Okay. So considering a number of ground motions, different ground motion sets, different values have come. This expression is perhaps the easiest, so we will use it. But there are other relations also available. So for 20% damping, can you give me R? Point 632. So this value will be multiplied by 0.63. It will be at 20% damping, it will reduce to 63%. So using this relationship, you can change the demand to whatever damping was, let us say here, suppose here the damping was 20%. So we will reduce it by 63% and we will get it. This is for xi equals 20%. What I have to do? I have to obtain intersection of these 2 points, these 2 curves, the demand and the capacity curve, in such a way that the damping at that point is satisfying both the curves. You understand? This is the demand. Demand also depends on damping. The capacity curve has different damping at different displacement. I have to obtain the displacement, one value of SD, which will satisfy both the curve and the damp. How can we do that? Can you think of some method? How we are going to do that? We can do that iteratively, easily. Let us say this is my bilinearized capacity curve, and this is my demand. Okay. What I will do, I will assume some displacement, some trial displacement, let us say SDO. I assume that this is the displacement which is going to occur in my structure. Then what I can do, I can develop the this hysteretic loop, and for this hysteretic loop, I can calculate xi total. I can do that. I can calculate xi hysteresis, added xi naught 5%. I will get xi total. Then I can calculate R xi, and with that R xi, I will reduce my demand. The whole curve will be reduced by that time. Suppose this is the curve. So I have assumed original point here, but I am getting the intersection here. What does that mean? That means the reduction is more. I have to do less reduction. My structure needs less dissipation of energy. Less dissipation of energy means what? A smaller displacement. So I will choose the next displacement somewhere in between these two. If I am taking this here, let us say earlier this was 20%. If I have reduced it here, what will happen to the damping? Equivalent damping. Is it going to reduce or increase? What will happen to the area of the hysteretic loop? The area of the hysteretic loop is going to reduce. And if area of the hysteretic loop is reducing, what will happen to the zygotal? That will also reduce. And if zygotal is reducing, what will happen to R side? It will increase. Less reduction. So the new response spectrum, I may get something like this. Okay. So here you can see it is very close. Otherwise you can perform another iteration. So by iteratively you will get the point where the damping for demand and capacity curve is same at that. This point we call performance point. Okay, and the corresponding displacement SDP, this is the performance displacement. What is this SDP representing? If I multiply this by gamma 1 phi 1 roof, then it will be delta roof at performance point. So this is the displacement expected to occur during the chosen earthquake. Whatever response spectrum I have taken, let us say I have taken it corresponding to dV, then this is the displacement under dV. If I have chosen MC, then this is the displacement under MC. Displacement of non-linear system, inelastic. Okay, and this is the most important point which we call performance point. That will tell us what will be the performance of my structure.
Sir,
Yes.
we reduce the demand at corresponding to the cycle what we have taken. But capacity of the building is also dissipate less energy because of that energy. Why and how is it possible?
Because if you are considering less displacement, the area of the hysteretic loop is less.
Typically, if the energy damping is less, this resistance offered by this structure.
Damping is not resistance offer. Damping is energy dissipated. Damping is not representing force. Damping is representing energy dissipated. So force is same. You can see that it is elastoplastic force is same. We have not changed the force. We have only reduced the energy dissipated. A which is given by the area of the hysteretic loop, it is forming at that distance. Force remains same. This SAY remains same.
If we have increased the time, then
If we increase the displacement, then area of the hysteretic loop will increase. Hence energy dissipated per cycle will increase. Hence equivalent hysteretic damping will increase. Hence total damping will increase. And hence demand will reduce. Okay? So we will continue from it when we meet now on Monday. चलो मैं ले लेता हूँ